So the second part of the notes, the second derivative test, supposing that f prime is continuous at c, if the derivative equals 0 and the second derivative is greater than 0, then f has a local maximum at c. The only time you actually use this is probably looking at a graph that we're going to look at next class, so I'll get into more of that with the next lesson, but just wanted to make sure you had the definition here. So, as I said, we'll get back to looking at local max and mins. If we look at this example here, discuss the curve with respect to concavity, points of inflection, and local max and mins, and then use this information to sketch it. So I already started it. If you want to pause it and work on it, that's perfectly fine. I'm just going to go through what I did here. So I took the derivative, as I said you always will do, set it equal to 0, and then again, correct notation, set the derivative equals 0. It implies that that derivative equals 0, and you can just put implies. You don't need to show any of the work. It equals 0 and 3. These are your critical points. With the critical points, we create our number line. I'm not going to show you plugging back in. If you want to do that, you're more than welcome to. If I'm going to go -1, -1 squared is positive, -1 minus 3 is a negative. A positive times a negative gives you a negative. 1 is a number in between 0 and 3. 1 squared, 1 minus is positive, 1 minus 3 is negative. That's also going to give you negative. And then 4, that's a number greater than 3. 4 squared, 16. 4 minus 1, 3. Positive number there. So we have the negatives, so we're going to put in our lines, negative, negative, positive. And notice that going from one side of the 0 to the other, we are going to have two negatives. That does not create any local max or min. That is a point of inflection. 0 going before 3 and after 3, decreasing to increasing. So we have a local minimum at x equals 3. And that's about all we can figure out from the first derivative. So the second part is that we are going to look at the second derivative. If we come over here, y double prime equals, just take that, 12x squared minus 24x. Set that equal to 0. We're going to factor out a 12x, x minus 2. And so we're going to get x equals 0 and x equals 2. As we said, that's a point of inflection. We knew that from already over there. So we're going to do another number line, 0, 2. This is going to give us our concavity. -1. -1 will give you a negative. -1 will give you a negative here. Negative times negative creates a positive. 1, positive, negative creates negative. And 3 will give us 2 positives. So there we go. If we want to look and sketch this curve, we're going to need to do two things here. One, our concavity interval, negative infinity to 0, or 2 to infinity, and concave down from 0 to 2. Notice that second derivative is always open brackets. The one thing I did not do with the first derivative here, we go back here, we can go increasing on the interval 3 to infinity. One thing I did not talk about yet is that when you look at first derivatives, we're going to do closed brackets, and we're decreasing on the interval negative infinity to 3. So we've got our concavity, we've got points of inflection, we've got critical points, we have our increasing, decreasing, and our minimum and maximum. So what I'm going to do again, as I did in the first video, is create the x and y axis and look at my intervals. So you can do that now too. A couple things that I did here while it was paused. We know that the y-intercept is y equals 0. Since we plug 0 back into this, we're going to get y equals 0. So 0 back into x, that's where the y-intercept occurs. And I also found the local minimum by plugging 3, x equals 3, back into the original equation. And we're going to get negative 27. So those are the two things I also did. So I created the xy axis, increasing, decreasing, concave up. 0, 0 is our point of is our y-intercept. We also know that's our point of inflection because at x equals 0 is our point of inflection. And we've got our minimum point here, 3. So if we look at it, decreasing, concave up, if we do our smiley faces, decreasing, concave up, looks like this. So we're going to kind of start here. decreasing concave up, until we hit our point of inflection. We're still decreasing, but now we've become concave down. So we notice that this was more of a smiley face. We're going to go more of a frown face here. And we know at 2, we hit another point of inflection, so we got to change back around to hit 3. The point of inflection is right about there. We start to decrease, or start to increase now that we hit our minimum value. Concave up, so smiley face, and we're good. So there's a rough sketch of what it looks like. Again, yours can be a little neater. I always do those small little lines just because that's the way I sketch, but that's what it will look like. You could have actually found the point of inflections and exactly where that 2 was going to be. I did not, but that's okay. And there's that. We're going to skip page 6, and we're going to go right on to page 7. And the last thing with page 7 is we're going to sketch the derivative here. So we have 3 graphs here. We're going to sketch the derivative. When you sketch the derivative, you're going to create another xy axis. We're sketching the slope. So at any point, you're going to sketch the slope. So the easiest slope, what is the slope at the minimum value? It's 0. So we'll sketch 0. The slope for this one is going to be positive. The slope for negative, or slope for this side is going to be negative. So notice that we're going to be below the x-axis and above the x-axis. So slope right here, it's not nearly as steep. So maybe right here, we're going to be up there. But the slope right here is extremely steep. It's going to be up there for it. And the same thing on the other side. And so if we look at this side, very little negative, extremely negative. You go on this side though. Extremely negative here. And so if we kind of look at this graph, extremely positive, extremely negative on the as we go to infinity, negative infinity, and very slightly as we go towards the middle, you'll notice that this creates what kind of curve? Well, if we look at this, it's much more of a cubic curve. And why is it cubic? Well, if we look at this function, it's not exactly a parabola. It's not a quadratic. It's a little narrower than a quadratic, which means it's an x to the 4th graph. And the derivative of an x to the 4th graph is a 3x cubed, or 4x cubed. Cubic, meaning that we should have the shape of a cubic. So again, when you're drawing derivatives, I always look to say, okay, what is the slope? Is it a little increasing or increasing at a steep rate? Increasing at a narrow rate or a steep one? Decreasing at the same way. And that's how I created the, this is the derivative, so this would be f prime of x. Let's look at the absolute value. What is this decreasing at? Well, if this is exactly the absolute value graph, then we know that this is y equals negative x. And you guys know that from your writing assignment that you did. So if this is y equals negative x, that's a slope of negative 1. Well, that means that if negative 1's there, that means that the slope never changes. So it's going to be negative 1 every place. It's just going to create a straight line at negative 1. Now, what we learned last time is that this is a corner, and a corner does not have a derivative. The derivative does not exist at a corner. It's a more appropriate way to put it. So we're going to have an open circle. This is y equals the x line, so we know that's a slope of 1. Again, an open circle. The derivative exists everywhere but at that corner, which is at x equals 0. So we have a slope of negative 1 when it's negative, and a slope of positive 1 when it's positive. And so there's the graph of the derivative. Just two different slopes. With this one, we have two slopes that are increasing. And they also are parallel, if you can see that. They're parallel slopes here. And so we're going to call that slope to be right around, I don't know, 1. Call it 1. I don't care if you actually figured it out. I didn't figure it out. It looks like it's about 1 though. Notice that a derivative does not exist at a jump discontinuity. So we're going to put a good old open circle there. And the slope is constant throughout anywhere except at x equals 0 from negative infinity to infinity. So that's the derivative. Open there, and the slope is just 1 everywhere else. And so that's how you can sketch the functions of derivatives. Again, always look at specific points. Positive 1, positive 1, positive 1, positive 1, positive 1. That's how I know it's a straight line. Hope that was informative for you, and I'll see you in class later.